So, welcome to MathStat341. This is lecture 30, give or take, day 30. What we're going to do today is we're going to prove the central limit theorem, modular results from complex analysis. I'm going to quickly redo some of the results we need, just to get them back on the board. Quickly review what we did for the Poisson random variable at warp speed, because this highlights what's going on, and then see what is the difference in the general case from the specific case. The specific case, we get to use nice features about the moment generating function of the Poisson. The moment generating function of the Poisson, we will see, is screaming, please take my logarithm. Right? In the general case, we will still do that, but it's not going to be as nice. Also, why do we care about the Poisson? We saw that you could use Poisson plus central limit theorem to deduce Stirling's formula. And so of all these sums of random variables to look at, there's a really nice application from Poisson. All right, so the first is the moment generating function of x is just the expected value of e to the tx. The next was the moment generating function of the sum was just the product of the moment generating functions of the individuals. Then we had the moment generating function of ax plus b of t. Well, if I just put in ax plus b, I get e to the tb, which I pull outside. And then it would be the moment generating function of x. And now I have an a, so it's evaluated at at. So these are the key results. And so by putting a bunch of pieces together, if we say x1, xn, iid, rv, and let's say zn is x1 plus xn minus n times the mean over sigma square root of n. So this was the standardization. We take our random variable. We know that the expected value of this is n times the mean, so just throw that away. And then this new quantity is going to have standard deviation square root of n sigma, because its variance is n sigma squared, because we have n terms. So we divide by sigma square root of n, so this now has mean 0, variance 1. And then the big result was the moment generating function of Zn. Well, the negative n mu over sigma root n, that's just taking the value of b to be square root of n mu over sigma. So you get e to the negative square root of n mu over sigma t. And then for all the other ones, we have a product from this, and then each one of them has a equals 1 over sigma root n. So we just get mx of t over sigma square root of n, and then we're going to raise this to the nth power. So all I've done is I've just written down on the board what we had before. Okay? It's just been a while, it's good to just have it back on the board. And then, if x was Poisson with parameter lambda, we had the moment generating function of x of t, I believe it was e to the, was it e to the lambda, e to the t minus 1? I think it was this. E to the lambda, e to the t minus 1. I think that was the moment generating function. Is that right?
That's right.
Okay. And then the mu was lambda. And was the standard deviation also lambda? Or was it the square root of lambda?
Just lambda.
Right, just lambda? Can somebody confirm if it's lambda or square root of lambda? Well, Poisson random variable.
The variance is lambda.
The variance is lambda.
So the standard deviation should be the square root.
And this illustrates one of the greatest things you can do. What should you choose for lambda?
1.
1. Why should you choose 1?
Variance, standard deviation are the same.
Yeah, then you don't have to worry about is there a square root. right? Because if lambda equals 1, it doesn't matter if I forgot the square root. If you took Math 150 and you did curves parametrized, and you often want the speed to be 1, that way you don't have to worry about, does my formula require me to divide by the speed? If the speed is always 1, doesn't matter. So just good things to just keep in mind. All right. So now, since it is paused, yes, it will not move. Excellent. So now we'll unpause it. Swing. Oh, excellent. Okay. It's a new toy. All right. So let's just do the proof of CLT for Poisson. So this will be really fast. If we take the log of the moment generating function of z and of t, we got negative square root of n. The mean is equal to lambda. And then we have sigma is equal to square root of lambda. So it should be square root of n square root of lambda. Hopefully this is right. Minus square root of n lambda t. And then when we take the log of the rest, we get plus n lambda e to the t over sigma square root of n. So t over square root of n lambda minus 1. And that's because when we take the log of this, the log of a product is the sum of the logs. The log of this to the nth power is n times the log of this. The log of this is going to just be, it's going to be lambda e to the t minus 1. But we are evaluating it not at t, but at t over sigma root n. Right, hopefully, I have not made a mistake. We get negative square root of n lambda t plus n lambda. And the n lambda should scare you because as n gets very, very large, n lambda is blowing up. But when we expand this out, the first term, the 1 is going to cancel the 1. So then the first term that survives is the t over square root of n lambda. The next term is going to be 1/2. So we'll have a t squared over 2n lambda. The next term will be a t cubed over 3 factorial n lambda to the 3/2, and so on and so on and so on. Now the negative square root of n lambda t, that cancels with this perfectly. So we're left with t squared over 2, because the n lambdas cancel. And this is another way to check and make sure that we actually got the standard deviation correctly, because I do believe in the central limit theorem. Not all of my colleagues at Williams seem to believe in that based on some of the grading distributions I've heard, but what about the next term? Well, we have the n lambda coming in. We will have t cubed over 3 factorial, and then we'll have an n lambda to the 1/2. And now every term from this point onward is going to have higher and higher powers of n. And because t is fixed, this is going to be dominated, and it's going to be negligible. And now you just need to do a little bit of analysis. One analysis you could do is you could say, look, I have all these 3 factorials and stuff like that over here. I could just view this as a geometric series where the first term is basically, t cubed over n lambda to the 1/2. So if you have a geometric series, I could pull this out, and I would have a geometric series that now starts at the constant term. That's going to be just some constant number, and I'll still have a square root of n lambda in the denominator. So as a nice exercise, and we'll do it in more detail later, you can show that all of this stuff doesn't matter. And in the limit, you get that the moment generating function of z n of t is converging to e to the t squared over 2, which is the moment generating function of the standard normal. And that's the proof of the central limit theorem for the Poisson. The proof crucially uses the fact that we knew the moment generating function for the Poisson. Because we knew it, taking its logarithm was trivial. And so we have that over here, we do some analysis, the higher terms don't matter. Now one of the things that's most surprising about the central limit theorem is the universality. It doesn't seem to depend too much on what distributions you look at. What distribution shall you not hope the central limit theorem to apply to? The quotient. If you need a distribution to be a troublesome one, go to the quotient. Okay, this should be your go-to distribution. What is so bad about the Cauchy distribution? I mean, Cauchy is one of the greatest mathematicians of all time. Yeah, it's undefined mean, you can argue if you want that the mean is 0, but it definitely has infinite variance. And so, given that we have things, that divide by sigma to normalize, if sigma is infinite, we can't really do any of these calculations. So the method breaks down. That does not mean that sums of Cauchy cannot converge to normal. It just means this proof won't work. It turns out that sums of Cauchy do not converge to normal. It's a stable distribution. Sums of Cauchy is Cauchy. You want to be very careful what you get. I have a lot of quotes from Mark Twain that I love. One of my favorites is, a cat that jumps on a lit stove will not jump on a lit stove again, nor will it jump on a cold one. For each event in life, only glean the lesson you should, something like that. So be very careful. We can't deduce that Cauchy plus Cauchy plus Cauchy plus Cauchy doesn't converge to normal. We just can say this would not show it. So if you consider most distributions have a mean. Most distributions have a variance. Most distributions even have finite higher moments. For a lot of things, we really only need to have a finite third, or sometimes it's third plus epsilon. Definitely fourth moment is often enough for the technical calculations. You need to show that this crap over here in the end converges. We will assume that all the moments exist. If I give you a probability distribution, let's say it has finite moments, is it a big deal to rescale to have mean 0? So what do you do to your random variable if you want it to have mean 0?
Divide by the mean.
No. Close enough. Yeah, subtract.
Oh, the variance.
Right. So we can just, a simple translation, adjust it to have mean 0. That's not a big deal. All right, now how do we make it to have standard deviation 1?
You just divide.
Now you divide by the variance. So the process of standardization, as long as the mean and the variance are fine, if I give you any distribution, you can always assume that I'm a nice professor and I have adjusted it so it has mean 0, variance 1. There are times when it's not convenient to do that, but we can assume that whenever we have a distribution that has mean 0, variance 1. So as we keep adding more and more copies to it, if we do this standardization, we can assume that the sum that we're looking at has been adjusted to have mean 0, variance 1. We're basically taking into account things that we know. What is amazing about the central limit theorem is that's essentially all we're assuming. And when you look at what's going on here, the third moment doesn't come in until we get to the t cubed term. And it's showing up here as a lower order term. We're dividing by a square root of n. So in the limit, the third moment does not show up. The third moment affects the rate of convergence, but it does not affect what it converges to. And that's why the central limit theorem exists. That's why you have this great universality. Why does every sum like this converge to normal? Because only the first two moments matter. It's harsh. I'm sorry, higher moments. But all that you do is you just affect the rate of convergence. You don't affect what we converge to. So that's the key point. And there are theorems that will actually tell you how rapidly you're approaching the normal distribution. And they will use as input the higher moments. But they will not affect the fundamental shape. Okay. Any questions about Poisson? Everybody comfortable with this? Can I erase this? So I'm going to leave on the board. So I'll unpause it for a second, walk over here, pause it. So I will leave all of this stuff over here, which is just a list of the fun facts we have. And now, what we'll do is we will apply it to the more general case. Okay, so the proof is going to be extremely similar, except for the fact that we no longer have an explicit closed form expression for the moment generating function. So all of this algebra is in the book. So if you do not want to write down all the algebra steps, if you just want to follow along, absolutely fine. Out of curiosity, how many people have an account with Amazon? I got an amusing recommendation that I might like the probability lifesaver, and it recommended that to me. It's an interesting algorithm. I'm a little bit curious as to why is it recommending it to me now? I haven't done any math looking recently with more Legos and stuff, but so we'll assume, x1 through xn, IID, RV, mean mu, standard deviation sigma, finite higher moments, the moment journeying function of all of them converges for the absolute value of t less than epsilon for some epsilon greater than 0. So we're going to assume that the moment journeying function exists in a neighborhood of t equals 0. T equals 0 is nice. What do we know is true for any moment journeying function at t equals 0? It's 1. The moment journeying function at 0 is always 1 because you're just taking the expected value of 1. Unfortunately, the moment journeying function does not always exist, but it will exist in the special case of t equals 0. Has to, no matter what probability distribution. It may not exist for positive or negative values of t, and that's the problem. But it will definitely exist at t equals 0. We are assuming it exists and converges in some neighborhood, that all the moments are finite. Well, if I'm assuming that the moment journeying function exists, that should almost imply that the moments are finite. I'm just throwing in assumptions. I don't care. Any distribution we look at, for the most part, is going to be true for this stuff. There might be a few that won't, but most of the distributions we look at will satisfy this. Those that don't, a lot of them would be fine if we used things like the characteristic function and used IT, not just t, and used Fourier analysis. We're not going to do that. So let's look at the proof. So we know mzn of t is equal to e to the negative square root of n mu t over sigma. And then we have the moment journeying function of t over sigma square root of n to the nth power. And so we start exactly as before. We look at the log of the moment journeying function. And it's going to be negative square root of n mu over sigma t. So we're a little bit worried about this term because this term is blowing up with n. But then we're more worried about this term, which is going to have a giant n in front of it. We'll have, n log of the moment journeying function at t over sigma square root of n. Now, because n is getting very, very large, this is close to evaluating the moment journeying function at what point? 0. And what is the moment journeying function at 0? 1. So if we just put in 1 here, this is going to look like n. This is going to look like square root of n, so this blows up, so oh well, we're dead. Oh well. Oh wait, we still have a good amount of time left. All right, so let's see if we can repair this. Yes, we would be dead in general, but we are dividing it by sigma square root of n. And so maybe we can start looking at a little bit of corrections as to how much is this changing as we move a little bit away. And maybe we're not so dead if it's 1. What is the log of 1?
0.
So if the log of 1 is 0, we actually have n times 0, which is 0, and now we're losing over here. So the hope is that if we're a little bit away from 0, there's going to be some decay from this. It's not going to be exactly 1 because the log of 1 is 0, and then this hopefully will all work out. Now the other thing, of course, is when t equals 0, we do have the log of 1, which is 0, which is bad. But if t is 0, this term doesn't exist. Right? So at t equals 0, everything perfectly cancels, and everything is still fine. We're worried that if we just naively approximate this as 1 when t is a fixed number because n is getting large, well, the log of 1 is 0. This is going to kill it now by a square root of n. So we need a little bit of better control over this. If we just call it 1, it's too crude. So we want to write that as 1 plus something. And we're going to use the log of 1 plus x. X is a bad variable to use because we have x already. 1 plus u is going to equal u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4, the Taylor series expansion of logarithm. So if u is very small, the log of 1 plus u is just going to be u. The log of 1 plus u, a little bit better approximation, would be u minus u squared over 2. And the hope is we don't have to go beyond the quadratic. When we get to the cubic, when we're putting things in here, we should be getting like an n to the 3 halves. Even when we multiply by the large n over here, we should be okay. All right. Any questions on how this is going? I have deliberately not looked at the algebra. Why do you think I have not looked at the algebra? So why do you think I haven't looked at the algebra?
You know the answer and it's tedious?
Yes. I know it works out, and I know it's tedious, and I know it's not pleasant. I have to do it once in class. I don't want to do it once at home. So let's just try to go through things. Now, the moment-generating function is the expected value of e to the tx. Right? So when we expand this out, this is going to be 1 plus mu t, right? The next term is the second moment, so it's going to be mu2 over 2 t squared plus mu3 over 6 t cubed plus dot dot dot. Now, that's the moment-generating function at t. We want the moment-generating function at t over sigma square root of n. So this is going to be 1 plus mu over sigma square root of n t. So I'm just replacing t, just putting the extra sigma. Plus the next one is going to be a mu2 over 2n sigma squared, right? T squared. And I'm not going to worry about the higher order terms. They're all going to be negligible. Okay? Now, let's look at the log of the moment-generating function of t over sigma square root of n. This is the log of 1 plus u, where u is equal to mu over sigma square root of n t plus mu2 over 2n sigma squared t squared, right? So I can now Taylor expand the log of 1 plus u. And the first term when we Taylor expand, there is no constant term. Good, because when t is any fixed number, as n goes to infinity, we're really evaluating this at something very close to 0. And the moment-generating function at 0 should be 1. So the log of 1 should be 0. So the first term we get is 0. Excellent. Now what do we get as we expand? Well, the first thing we get is we get u minus u squared over 2 plus u cubed over 3 minus u to the 4th over 4. And let's think about this. Notice for the u's that everything has at least a t in it. Right? So over here, the u squared, everything's going to have at least a t squared over n. Everything here is going to have at least a t cubed over n cubed. I'm sorry, n to the 3 halves. Everything here is going to have at least a t to the 4th over n squared. We multiply at the end of the day by n. So really, let's put in n times the logarithm. And so even when we multiply by n, the first two terms we have to worry about, because the first term is of size 1 over square root of n. So when I multiply that by n, that can still contribute. The second term is of size 1 over n. When I multiply that by n, that can still contribute. But the next term, the t cubed term, I don't have to worry about. And then the other thing is you have to look at, well, what about cross terms and whatnot? If I now look at, cubing something, I could have this factor 3 times. I could have this factor twice and that factor once, and all those different combinations. The whole point is none of that other stuff matters. is you basically want to show that u is less than equal to, say, some constant over n to the 1/2. And it doesn't seem like that should be an unreasonable thing to show. We've got something that's bounded by a geometric series. I can even drop the factorials down below, and I'm okay. When n is really, really large, well, but the moments are growing. But I know the initial series converges. So this is where you use some real analysis. If there is desire, I am happy to go through and do this. My feeling based on previous years of teaching this class is there really isn't that much interest to see this. That the moment generating function converges, that means the series converges. If the series converges, then from some point onward it has to be sufficiently small. And you can show that if the moments are finite, there should be some control over what's going on. As n goes to infinity, I can make these small. And if not, then if I just assume a little bit more, maybe the moments don't grow too fast, I should be okay. And so we should be able to use this as an input. If you want, as a nice exercise, try to prove something like that and see what do you need to actually make the proof work. But the point is, each one of these terms is gaining an extra square root of n. The moments can be growing, but we also have factorials down below. So in fact, if you want the moments to grow, the moments can grow so long as they're not growing so fast that they kill factorials. And we know the series converges because I'm assuming the series converges. That gives me some constraints about how fast the factorials can grow. If you put in t equals 1, for instance, or t equals epsilon, it's going to be converging. And so that will give me some growth rate over the means and the moments over the factorials, and from that you can get a bound like that. Is this enough detail? Okay. So now that we have that, because u is bounded by something over n to the 1/2, when I get to the cubic term, it's not going to contribute. Because this is going to look like something over n to the 3/2. Even when I multiply by n, it's going to be insignificant. Same thing. So what I can basically do is I can say, screw this, you guys don't matter. Plus something over n to the 3/2. And I won't have to worry about that anymore. All right, now we continue. So the first thing is now we have n times u. Which parts of u are going to matter? I don't care about the t cubed and higher. Because the t cubed and higher are going to have at least an n to the 3/2 down below. And when I multiply by n, it's still going to be small. So the first term, I'm going to have n times this. I'm going to get nu over sigma root n. So I'm going to get square root of n u over sigma t, which makes me happy. Doesn't take much to make me happy. Right? Children not fighting, happy. A lot of times, yes, I know what they're doing is dangerous, but they're doing it together. This is going to perfectly cancel what we had from that b. Wonderful. So we don't care. The next thing we do is now we have n times this term. So the n is going to cancel the n down there, and we'll have plus a mu2 over 2 sigma squared t squared. And then we don't care about the rest over. Now let's look at the minus n times u squared over 2. When I square u, I don't care about any of the t cubed terms. I don't even care about a t squared term, because if a t squared term either hits itself or a t term, it's going to be a t cubed term, and it'll be divided by an n to the 3/2. All I care about is when ut over sigma root n hits itself. And so I'll get a mu squared t squared over sigma squared, and then I have an n, but the n cancels that. Plus mu something over n to the 1/2.
Wait, there's also an over 2 in the third thing? Because
yes, thank you. Because there was a 2 over there. Yes, and that is extremely important. Without that, everything breaks down. Okay? We are almost there. So we now get, oh, wait a minute. Yeah, okay, this is the log of the moment generating function of x. we wanted the log of the moment-generating function of z, which differs by having this extra piece over here. So we now get the log of the moment-generating function of z on t. The pieces cancel. We'll have a mu2 minus a mu squared over sigma squared times t squared over 2 plus the mu something over n to the 1/2. That is not a good looking 2. That's a much nicer 2. Okay. What are we hoping that the moment-generating function will look like? What's the moment-generating function of the Gaussian? So the moment-generating function of the Gaussian is e to the t squared over 2. So what's the log of the moment-generating function of the Gaussian?
T squared over 2.
T squared over 2. We almost had a t squared over 2. We missed by 2 things. We have a factor in front of it, and we have this crap over square root of n. Well, the crap over square root of n doesn't matter. That's going to go away in the limit. But we unfortunately have mu2 minus mu squared over sigma squared. What must mu2 minus mu squared over sigma squared be?
What?
Better be 1. Is it 1?
Yeah.
Yes. What is mu2?
Second.
The second moment. This is the second moment minus the square of the first moment. What's the second moment minus the square of the first moment? The variance. This is just the variance. This is just sigma squared. And so this does converge to t squared over 2 as desired.
That's the central limit theorem.
That's the central limit theorem. And we did it, we kept this stuff on the board, but we basically didn't have the blackboard space of a dorm room. It's a little bit misleading to say dorm room because people do not really sleep in this room, hopefully. Why were we able to do the proof so quickly? You don't get the title central limit or fundamental theorem lightly. Why are we able to do the proof so quickly? So one thing is we assumed convergence. We assumed that the moment-generating function was nice, which allowed us to say we can throw away various things. And in fact, it would even stop this argument. So a lot of times mathematicians play these games, oh yeah, well I can prove this thing with the following conditions. And if you've ever seen the TV show Name That Tune, so people compete as to how many notes of the song do they need to correctly name the tune. I can name that tune in 4 notes. I can name that tune in 3 notes. I can name it in 2 notes. Name that tune in 2 notes. And they play you like 2 notes, and you see if you can do it. There's a desire to prove theorems in the greatest possible generality so that in whatever setting you're in, you actually have a chance of using it. When I was young and an undergraduate, I was always furious when we assumed things we didn't need. I wanted the proofs in the greatest generality possible. Then when I went to grad school and started doing real research, oh yeah, my function's infinitely differentiable. Yeah, that's not a problem. What do I mean this twice differentiable? Yeah, no, it's infinitely different. Because I was actually trying to use the math to do something. So we have definitely made some big assumptions. You can remove them at the cost of more work. What else allowed us to do the proof so quickly? And we've got this basically like 2 boards. Yes?
Well, I guess it might be like all the stuff we did beforehand.
Yeah,
The whole board.
right? We paid the price earlier. We proved all of this stuff. Now, were these proofs hard? I will admit, I don't remember a lot of these formulas. A lot of them I just derive as I'm doing it with you. For instance, what is the moment-generating function of ax plus b? Well, I know the definition, so let me just put an ax plus b and say, oh, we get tb, I'll just pull that out. They'll have e to the tax. Oh, okay, so it's just the moment-generating function not evaluated at t, evaluated at at. I should probably have this memorized, but I can derive it so quickly just by looking at that. So this one is actually not too bad. This is the definition. We'll get back to that one later. What about this one over here? Was that any work to prove? No. That the moment generating function of a sum is the product of the moment generating functions. Basically, it came from linearity of expectation. And no, so not linearity of expectation. The expected value of products are the products of the expected values if they're independent. So by assuming independence, this actually wasn't that bad. This is then just standardization. And then this is just substituting in. So it's really worth, when you have a big result like this, going back and thinking. The key idea is to look at this moment generating function. So remember, we had Professor Montgomery come from Michigan and he gave a talk, and he talked a little bit about generating functions. And it is incredible how powerful generating functions are. If you look at the right object, then everything is there for the analysis. And that was what was going on here. Is by looking at the right function here, everything flows nicely without too much work. And it really is a follow-your-nose proof. Is anybody interested in knowing a probable problem on the final exam? Okay. Modulo, of course, the fact that we actually don't have technically a final exam in this class, but I do not know what the final is. I always write them before the semester begins. But almost surely there will probably be something like, take the central limit theorem, and here's a probability distribution, and show that the central limit theorem works for that probability distribution. Which distribution will you not get? Right. You will not get the Cauchy. What else will you not get?
Poisson.
Probably not the Poisson. Why? We just did the Poisson, okay? So I'm probably not going to do that. But I will probably give you another probability distribution. What would you need to do? Calculate its moment generating function, and then go through the argument. And then what I don't want you to do is to just repeat this argument and then at the end of the day put in the values of the mean and the standard deviation for. I want you to actually use, so I want to make sure that there's no misunderstanding. I want you to use specifically, explicitly, the moment generating function of the distribution you're looking at and bypass all of this. And the reason is we did not fully deal with all the algebra in all of its glory, right? We stopped and we didn't show how this is small. Yes?
How much limit convergence stuff should we try to show as much as we can?
Show as much, and if you have any questions, just ask me.
Okay.
But it's not meant to be anything onerous. For the Poisson, it wasn't bad.
Yeah.
So I'm going to give you something that's nice.
Okay.
Well, at least I hope I gave you something that's nice. That was previously. I don't know what was chosen. But the goal is to just show me that you understand the argument and you understand how to use it. Right? This is why I'm not giving you a tremendous amount of homework on the problem. This is why I'm alerting you to what's coming. If you can do an argument like that, you'll be fine for that question on the exam. I just want you to know what generating functions are, how to use them, and then if you have an explicit form of the generating function, you can often bypass a lot of the technical conditions. Okay. Any questions on this? So this finishes the unit on proving the central limit theorem. And we've even seen applications of the central limit theorem. You can push this in many directions. In more advanced classes, you might go, well, what if there was some dependency? What is still true? Or what if the random variables are not identically distributed? And there are still central limit theorems in situations like that. And then the question is just, how far can you push and still have a central limit theorem exist? But now that we have this, this is one of the big tools in all of statistics. So the next question is going to be rates of convergence. So how many of you have taken a stats class? Okay, other than this one. You're taking this one, you haven't taken. Okay, so in a stats class you have finished, how many of you have used hypothesis testing involving normal distribution? Okay, what do you need n to be safe? Around 30. Why? Why?
Because otherwise that like stuff doesn't go to zero as quickly.
And so 30 is good enough?
It's just realistic.
Why is it realistic?
In a real life setting, you can't expect millions of data points.
Sure you can. Now, you may not always be able to get them, but for some things you can easily get millions. We can do simulations for a lot of things. Or but instead of doing 30, we might say, we can't really be confident until we have at least 50. There's a lot of really bad science done where you don't have sufficient numbers of people in all the different cells. And you're trying to look at all the different things. Did I tell you about the child autism and TV study? So when Kim was very young, I saw a study by some economists linking the amount of TV you watch to child autism. And the more TV you watch, the more likely you are to be autistic. And as a parent, what is my first thought?
Absurd.
I'm sorry?
Absurd.
No.
No TV.
Yes. So, first thought, no TV, no YouTube, But, now that Kim is safe, then I go to my second thought, which is
Absurd.
absurd. Okay, let me look at the study. So, this is a study that claims child autism is caused or exacerbated or made more likely by watching TV. What data would you expect the study to have?
How much TV children watch?
How much TV children watch and?
Prevalence of autism.
Okay, interesting. We could actually go back and see how many seconds it took. I think it was less than 10. They did not have that data. They had autism, which they had your half, but instead of your suggestion of TV watched, they had precipitation. The more rain, the more snow, the more likely the kid is to be inside. The more often the kid is inside, the more likely they are to be watching TV.
Wait, I think the cause and effect is kind of wrong there.
It's like one of the worst proxy variables.
So,
Well, like,
what happened after I read the paper?
More TV.
Yeah, okay, let's go back to watching TV, let's go back to watching, YouTube. And again, the reason they did this is it was very hard to get data on how much TV a child watched. They were looking for a proxy variable, and they thought that this was reasonable.
but then like, why doesn't that show that like if it rains more than the child,
There are so many flaws with this, okay? I think they might have just been looking at total precipitation. So if you have a couple of really bad days, that could be worse, according to their metric, than just a couple of days that are spread out where it's raining during times when the kid might be outside. There's a lot of problems with this study. It's not the worst that I've seen, but it is close. I actually had the worst one a moment ago. I remember the worst interview question I've heard, but I will try to remember what the worst study I was. This is towards the top of the list in terms of it's not getting the data that you want because it's hard to get the data. And so what data can you get? What can you do from that data? And you have to be very careful about the conclusions you draw. The worst interview question was either after 9/11 or after the first Gulf War. After 9/11, they asked somebody on, this was one of the big 3 networks, they talked to an airline pilot, and they said, do you have any ways of alerting people on the ground that there are terrorists trying to take over the plane, ways that terrorists might not know about? The airline pilot very quickly said, there are technical reasons why we can't have any system like that. What's your next question? And just try to. The other one was after the first Gulf War, there's a 8 or 9-year-old girl whose mother's serving in Iraq. And she's being interviewed, and the reporter asks, if you could have one thing in the world, what would you wish for? And what do you think the girl wished for? Her mom to come home safely. And she says that through the tears. And the reporter goes, alive? So, hands down, it's tough between the two. I mean, the alive is the most insensitive, but the first one has national security implications, and lives are on the line. So I don't know how you score. Different people have different metrics. They're both really bad. you need to be careful about what studies you're looking at. And sometimes the studies don't have the data that you want. Why do we take 30? Well, for a lot of distributions, once you have 30 points, that's enough that a lot of these terms are pretty small, and you can assume that the central limit theorem is either kicking in or is approximately kicking in, and it's not horrible to use this. But you've got to be careful, and if you've taken advanced statistics courses, you sometimes use refinements. You might do a t-distribution, where you can do things other than just using the normal and the central limit theorem. But I want you to be aware that what's going on is we have these higher order terms that for the most part don't really matter as n gets very large. What do we consider very large? The hope is that you can get by with n around 30. That's a reasonable size, and that you have a chance of actually getting that in the data that you're collecting. A lot of times we don't have the ability to get that many elements in a cell, and when we don't have that many elements in the cell, then you get a little bit worried as to have we gone far enough that we can trust what's happening. All right, so I will turn this off now, and I will ask you the complex analysis question. So